Okay, so I just want to point out it's available. I'm not going to go back through it, but where I made the typo copying down my numbers and was unable to recover in real time, I went back and redid the matrix and then checked all the stuff and then went through the process of given, in principle, a large rectangular matrix with dependent columns, how do you find an x such that ax equals 0? And the LU factorization is the way to go. And so I've got all the numbers right now. It's available at the end of yesterday's lecture. Okay, so just letting you know it's available. We're now working on norms and least squared error. Norm of a vector was the sum of the squares of the component's square root. And what we're going to be looking at is how to find solutions to equations that don't have solutions. So there can be approximate solutions, and we're going to approximate them in the best possible way that we can. Okay, so we're looking at ax equals b. B is not necessarily a linear combination of a. And the big application we'll have fun with is linear regression, fitting functions to data. And that's really the underlying technology for machine learning. It does a nonlinear twist on that, which you can learn in EECS 445, but we should be able to make a sophomore level available when the Robotics Institute gets its undergraduate program available, because you guys will have all the tools to start doing that. So here's what we had. We had data for which there is no line that goes through all the data points. The data is x is 137, y is 245. We're trying to fit a linear model to it. And our unknowns, because it's just a simple linear model, we don't know the slope, and we don't know the y-intercept of a line that would, is that the best approximating one? Is that the best approximating one? We'll find what best is and then solve for the coefficients. So first, just setting up the model, and I maybe skipped a step, so I put them all in here now. We're going to write yi is mxi plus b, where the x and y's, this is our first data point, second data point, third data point. So I just write down y1 is m1 x1, y2 is mx2 plus b, y3 is mx3 plus b, and I put them, stack these up in a vector. And then I do what we did in week 1 of the course. I write this as a matrix times my unknowns. My unknowns are the slope and the y-intercept. And if you want to put them in the opposite order, it's fine. That would move this column to here and this column to here. It doesn't change the equation. You put the unknowns in any order that you want. But the thing is, when you're done, you end up with a column vector, a rectangular matrix we're calling phi for the moment, and as times a set of unknowns. And so the equation looks like this. And for us, y was 245. I plug all in all the numbers. The x1, x2, x3, I plug those in. And then I have a column of 1. And where does the 1 come from? It's clear that m is multiplying the x's, but b is multiplying a 1 here. Okay, so that's where that came from. b is multiplying a 1. b is multiplying a 1. So I get a column of 1s when I have a constant. If it depends on x's, a little bit later, we'll have x squared terms in here. We won't limit ourselves to just fitting a line. Okay, so that's where we're picking up. We're good? Ready to rock and roll? Okay, so when you're first learning something, notation is everything, right? unfamiliar notation just kind of throws you off your game. So let's put this in notation that we're more comfortable with in Rob 101. Whoops, off your game. Okay. So let's rewrite as AX equals B. Okay. What is the A? What is the X? What is the B? So the original equation was Y equals phi times alpha. So what we have is A is the matrix phi. We'll call that a regressor matrix later on. Whoops. X is alpha. Okay, that's our unknowns. Okay. Not being called X. They're being called slope and offset. That's fine. Okay. And then finally, B is equal to Y, which is our function, our measured data. Oh, man. Okay. Okay, so let's just play around with this. And so here's our point. There is no line that goes through all data points. You know, that might have been a mystery to us when we were 6 years old, but it's not a mystery to us now, okay? We get it. 3 points generally do not lie on a line. Okay, so if there's no line that goes through them, that means there is no solution to our equation. Okay, so when we were younger and more tender, as soon as we got to that stage, we just said, we're done, okay? There doesn't exist a solution, let's just move on. But we're now more mature and ruggedized. We want the line that best fits the data. So we need to figure out what we mean by that. Okay, so I'm going to write, and I'm in two minds about my notation, but I think I'm going to call it this. This is a function that depends upon x. I want to write it like that. Okay, so this is the error in the solution. And it depends on the x I choose, right? Okay. So for some x, e of x by definition equal to ax minus b might be huge, you know? I just plug in Avogadro's number in every component, and I might just get ginormous numbers out of there. So maybe that's not a very good choice, right? Okay. And then for other x, e of x by definition equal to ax might be smaller. I mean, if I take x equals 0, the error is no bigger than the length of b, the norm of b, okay? So how can we find, so here's the big question, and this is super cool question. Can we find an x that makes the norm of the error as small as possible? Inquiring minds want to know, can I find one that makes the norm of the error, the sum of the squares of the components of the error, square root, as small as possible? Okay. And if so, is it unique? Or could there be 37 different possibilities, all of them giving us the same error? Okay? Okay, so the answer is sort of like the best possible answer you could possibly get. Okay. It says this. Suppose the columns of A are linearly independent. You catch up. Okay, just remind you, we're looking at an equation roughly that says ax equals b. So we just moved the b on the other side so that 0 is, you know, if we got 0, we'd have a solution. And if we get e small, that's a really good solution perhaps, okay? But we know that when we're looking at things like this, we need the columns of A to be linearly independent for uniqueness to happen, okay? So that's where that comes from. We're looking at this. If there's going to be any kind of uniqueness for what the product A times X is, the columns of A have to be linearly independent. So it's like a minimal hypothesis here. Our hypothesis, suppose the columns of A are linearly independent. Then there exists, yep, this is like a theorem. X star in Rm such that the norm of my error when I plug in x star. Okay, so what is that? That's norm a x star minus b. Look at this. It's less than or equal to the norm of ax minus b for all vectors x in Rm. Okay? This is the best you can possibly do. You can find this vector, x star. When you plug it in, the error in the equation is smaller or equal to the error you get when you put in any other value. Whoops, don't do that. I thought it was this. Okay, you put in any other value, all you can do is increase or keep the error equal. You can't make it smaller. This is the best one, okay? So it is a minimizing thing. And then the cool part, moreover, x star is unique. There's only one of them. Okay, so when you're looking for something and there's a whole bunch of them, your algorithms get confused, and when there's only one thing you're looking for, it's much easier to have your algorithm focused on doing that. So that's cool. Okay, columns of A linearly independent. There does exist a vector in Rn that minimizes the error in the equation. So there is no exact solution, but I can make the error in the solution as small. I can minimize that error, and I can find a unique vector such that that error is less than or equal to the error for any other vector x in Rn. So let's kind of make sure we've got what this means, okay? So meaning, and I'm going to introduce you to some of the most powerful notation in all of engineering is coming up here. Okay, so meaning, when I do norm of ax star minus b, it is equal to the minimum of the norm of ax minus b, where I search over all points in Rm. So A is n by m. B equals n by 1, okay? Our usual size thing. So x star minimizes the norm of the error. So that's why we introduce norms. We know how to talk about the length of the error, okay? And this deserves an exclamation point, maybe two of them. Now, this notation, this is the error that's being minimized over all points in Rm, and this is the resulting value of the error. I want a notation that tells me I'm looking at the x star now. Okay, so I'm going to write it down, and then we can talk about it. Okay, one writes, and this is super important and awesome. X star is argument min x an element of Rm norm ax minus b. Okay, so many cool engineering problems can be posed as, I want to minimize something, and I want the output of my process to give me the value that achieves the minimum. That's what this notation means. Arg min is the argument of the function. Okay, we're minimizing over all of these x's. When I write it like this, I return the minimum value of the function that is being minimized, but I'm not returning the point at which it's minimized. The function has a smallest number, 3, and I'm returning that, but it happens at x equals pi over 4. I want to return that. That's what this does. That's the point at which the minimum is achieved, okay? So x star is that vector in Rm achieving the minimum error, okay? Okay. So you can blow away all your faculty and your other courses when you start writing, oh yeah, I guys got it, here's my function, x star is arg min. I mean, it's up to you. You're writing your function. You can put return just the value, and then you've got a minimum, but you can put return the x, and then you've got the argument of the minimum. So we'll keep pounding this in, but it's a really important new concept of a function, okay? The argument of my function, that is minimization, is the value that achieves the minimum. Okay, maybe I beat that into the ground enough. And so now we want to know how to compute it. Okay, and the answer is too simple to even believe. Okay, you're not going to believe it. Okay, it's just too simple. So, but I'll write it as a more or less a theorem fact. Suppose the columns of A are linearly independent. So you cannot give up on that hypothesis. We could still then find a minimizing thing, but it would not be unique, and it really messes everything up. Are we good with TFAE? The following are equivalent? Okay, cool. 1. This is the guy we're after, or the gal, the object, arg min. We're looking over a huge set of possibilities, and we want the value that makes this error as small as possible. So that's one thing. This next one tells us how to compute it. 2, A transpose A times X equals A transpose B. Whoops, I can put a star here. What did I do? I have AX equals B, and I multiply both sides by A transpose, okay? That's why I said it's too simple. You can't believe it's possibly true. You solve that equation, and you have it, but it's true, and I'll show you why, okay? You only get, part of the why. There's even more awesome reason why in a higher level course, but it's already not bad for Rob 101. Okay, so these are equivalent. Now, look at this. We're inverting A transpose A. Are we allowed to do that? Well, we assume the columns of A are linearly independent. How did we test that? All last week. We formed A transpose A, and we took its determinant. What we really did was LU factorization and look at zeros on U. Same thing, just because we don't like to do determinants of 19 by 19 matrices, but LU factorization of that is a heartbeat. So recall, whoops, my little vanishing detective ink trick. Determinant A transpose A not equal to 0 if and only if columns of A are linearly independent. Okay. So it's turning out very, very useful to have this notion of linear independence. It just kind of helps you state hypotheses and then understand what's going on. Okay, let's go back and solve our line fitting problem using this formulation. Okay, I'll plug in all the numbers, and then I'll give you some insight into why. I mean, it's just too good to be true. AX equals B does not have a solution. Columns of A linearly independent. I multiply through both sides by A transpose. This equation is now square. A transpose A is invertible because of my solution. Fine, but why in the world should that be the minimizing solution? It's not at all obvious, okay? It's pleasantly true. It's so amazingly simple to compute, but it shouldn't be true. It's too good to be true. Okay, let's go back to our line fitting problem. Okay, and I'll write it out, not in terms of the 1, 1, 1. B was 2, 4, 5, yeah. And then the X was the slope and the intercept. But when we start doing really regression problems, I'm going to encourage us to go back and just get used to this kind of notation. So, you know, AX equals B for us will be the same thing as Y equals phi times alpha. I mean, it's totally arbitrary to put the X on the right. We can put the B on the right. We can put the B on the left and the AX over there. It's still an equation, okay? It's just that everybody in the world writes that, but this is how you tend to write regression problems. Your data that's measured for the function values on the left, the regressor matrix you build, and then your unknowns on the right. I don't know, it's just a habit people have, okay? So to apply our answer, we need to calculate A transpose A times X star equals A transpose B. So that's all we've got to do. And see, we get 1, 1, 3, 1, 7, 1 for A transpose. And this was A. And I checked my calculations this time. 59, 11, 11, and 3. Okay, so that's just Julia It's done before you can even possibly understand. We need A transpose B, so that's A transpose again. Of course, Julia, you never write any of this stuff down. You just do the, whoops, the A and the B. So this is 2, 4, 5. You get 49 and 11. And then you solve your equations using any method you want. And you get x star equals 0.46 roughly and 1.96. And I'll remind you that this is the slope and this is the y-intercept. Okay. And I got a plot of that. So, whoops, wrong place. Insert image file. Have enough room here? Yeah, I think so. Line fit, open. Figured you guys had suffered enough with my poor drawing skills. Okay, there's the line. It minimizes, you calculate the distance to the error there. You sum up those errors, you square them. That's the line that minimizes the total error, squared error. Amazing, huh? Okay, so seems like it's easy to do. Building the regression problem takes practice, but once you have it, you know, you may not like the y, phi, and the alpha, then just do it. A and the x and the b. Who cares, okay? But you just, more you do it, the easier it becomes. You check that the columns of A are linearly independent, but the way we always check it is we form A transpose A and we do an LU, and so we're all set up to solve this equation. Okay. Can I take questions before I move on and sketch out why it's kind of true? Because it seems like, poof, magic. It is magic. Everybody's ready for why it's true? Okay, so I'll just give you a brief idea. All of the details are in the book under optional read. Why true? The proof technique is almost the same as how you derive the formula for the quadratic equation. So in the book, I go through the derivation of the solution to the quadratic equation. You use a method called completing the square. This is a completing the square, but it's a vectorized version, but it's the same thing. So it kind of hurts your head, okay? Okay, so here are the steps. 1, x star equals arg min x in R, norm of ax minus b. This is equivalent to something slightly different, but x star equals arg min, still x in, whoops, rm, but I'm going to square the right-hand side. And I want an extra line there. So the square root function is monotonic. It goes like this, okay? And so it preserves the order of where the minimum is when you square it, okay? So if you do a bowl-shaped thing, and then you take the square root, it kind of flattens out into lines, but the minimum still stays at the same place, okay? So you need to play around with that a little bit. But whether you minimize the norm or the square of the norm, the square root doesn't change. It does not change where the x occurs that's doing the minimum. So that's the first thing. So this is why it's called least squares, because people typically write it down with this, because that has the sum of the squares. Now, we talked about that the square of the norm is the transpose of the vector times the vector. So here's the vector. It's ax minus b. We transpose it. So that's what we're trying to minimize here. This guy and this guy are the same. Now this is where it gets painful. Some painful algebra to complete the square. So it's, and if you go back to the quadratic equation, it's a little painful too, to complete the square. And we're not going to go through that. But this is what you get. Okay, let me pause, because this is kind of our drop the mic moment here. We take ax minus b transpose times ax minus b. Whoops, no transpose there. Slow me down. Is equal to, and I need to write this very carefully, a transpose ax minus a transpose b transpose times, oh, I want to put that in a different color. A transpose A inverse. Okay, I want to keep the focus on what we're trying to minimize here. A transpose AX minus B plus B transpose B minus B transpose A times A transpose A inverse A transpose B. Whew. So going from what's on the left to what's on the right, that's about half an hour of algebra, okay? So, but it can be done. But why is this interesting? This does not depend upon x. Okay. So you're choosing x to make everything here. You're trying to make this plus this as small as possible. I don't care what x you change, this is just a constant. It's just sitting there. So you look to this part and you see how to choose x to make this part as small as possible. Well, oh, I left out an A transpose. Look, if I can set this to 0, like I made that part as small as possible, okay? And that's the solution, okay? That's the solution. That's the solution. That's the solution. A transpose AX minus A transpose B equals 0. That's the solution. Okay, so that's what the completing the square tells you. This you make, so you minimize with A transpose AX minus A transpose B equals 0. And that's why that formula is true, okay? The formula is so simple, but it takes quite a bit of work to get things in that form. So you guys want to go through it, it's in the book, but you don't have to. Questions on least squares? Just need practice. Okay. Let me get out of drawboard for a little bit. Tablet mode. No. This is Julia. So, what can you guys see? Not very much. Can you see that? That means at home they can probably see it too, okay? So that's just my usual stuff, you know, calling the linear algebra package random because we like to choose big matrices and we don't want to put a whole bunch of numbers in there, so we just choose some random numbers and create large matrices. LaTeXify is because when I like to do things, I want to print out and put them in the book. I want it set very nicely, etc. Okay, so bingo. So we'll do this first function. The function is, on the first line, f of x is x plus 3x squared minus x to power 6. Now, in a real problem, you do not know the function that is generating the data, okay? So I shouldn't have even let you see this, okay? But this is how I generate my data. Putting x min as -2 and x max is 1. I build a data vector that goes from x min to x max in increments of 0.1. And then I'm going to add noise. I'm going to simulate my error, my measurements not being perfect. We call it noise, okay? And then I'll do scatter plot. So let's just run this. Okay, so here's my data. Now I want to fit a function to it. So imagine this is what you've done. This is the equivalent of getting the dots for the fitting the line. So I'm going to use monomials. So monomials, if you've forgotten that term from algebra, it's the powers of x. So the 0th power is 1, the first power is x, the second is x squared, etc. Those are monomials. Okay. I'm going to build my regressor matrix with, so I'm going to do a polynomial that looks like 1 with a coefficient plus x times a coefficient plus x squared times a coefficient times x cubed as a coefficient. Okay, you see that? So my regressor matrix has a column of 1s, it has a column of x's, it has a column of x squareds, and a column of x thirds. And you can see up here that we can do even more, okay? Look how hard it is to add additional terms to my regressor matrix. Not that hard at all, okay? And I want to solve phi transpose phi equals phi transpose times y. And I should have done it by LU, but I didn't have time to put all the code. So I'm going to cheat. I'm going to do something that I'll slap you on the back of the hands for doing. I'm just going to use the inverse function. It's wasteful. But on this little tiny problem, it doesn't matter. I will then get my estimated y's. I'm calling them y hats. A little hat over it is what engineers tend to use to mean an estimated quantity. Okay, so I have my true value and I have my estimated things, and then I'll plot those. So, and, not bad for a first shot, okay? But, thank you for playing. Let's uncomment this one and comment this one. Now, I forgot to emphasize, why do I have this dot before the circumflex and then the power? So how does Julia know to apply something to each element of a vector? You need to tell it that, if you just do sine of a vector, Julia goes, bah! You go sine dot of the vector, then it does sine of every single component. So the dot says, do the operation on each of the components. If you don't want to use the dot, you need to put a for loop and do each of the rows. That's fine. So you can build it by rows, and I'm just building it by columns, okay? And I use this vectorized ability in Julia, in MATLAB, and almost all of these nice languages, okay? Cool. Whoa, okay. That explains my data pretty well. Not bad. Questions, or you want me to keep going? You get the feel how this is a powerful tool? You've got data, you want a function that explains it, okay? I'm going to give a more complicated function now. Okay, let's fit that one. Okay, and don't be greedy. Whoops. Don't need to comment it out, but I will. Okay, let's see how we do. Oops. Yeah, okay. Huh. So this one does really bad. I mean, how do you know how many terms to include? I would be licking my finger and holding it up and let the wind blow, okay? So this is where engineering insight comes in. You need to play with the data to see, okay, what's going on. Not too bad. Okay, not too bad. Now I'm going to make my region bigger, so it's a tougher problem. So there's my data now. Ooh, it gets really funky, okay? Can a few monomials match that? Look how good we did with this one. Oops. Okay, so your guys' project 2, it'll be coming up. These monomials, for little toy problems, they're good. For something real, like you would attack with in artificial intelligence and machine learning and stuff like that, there's another class of functions that you've never seen before. They're called radial basis functions, RBFs, okay? Once again, I'm giving you the keys to the kingdom so that you can now have these. If you don't know about the function, you can never use it, okay? We're going to, in project 2, we'll give you just small data sets where you tune by hand the coefficients and do a regression by hand and just fit, okay? You build up your intuition for these radial basis functions, and then we go at scale. And you're going to be building a precipitation map for the state of Alaska. If that sounds crazy, it is. It is totally, awesomely crazy. Okay, you'll have thousands and thousands of data points, but it'll be a smaller data set than you had for your LiDAR data, okay? So you're gonna learn about these a new class of functions called radial basis functions. So that's the end of our exploration of regression. And we've now crushed the life out of what you know about monomials. We don't like them.